Okay, this is project test 4, video number 4, questions 31 to 40. And this video is going to be a little bit longer and some of the problems a little bit more challenging. So the height of 3-year-old boys is approximately normally distributed. Duncan and Shane are 3-year-old boys. Duncan is 32 inches tall, and this is the 32nd percentile of the distribution. So I'm going to go ahead and draw a picture of kind of where that is. So this area right here is 0.32, and he is at he is 32 inches tall. All right. And then Shane, although the distribution is the same, I'm going to draw it on a different graph. Shane is 34 inches tall and is at the 62nd, so he's over halfway. So this area right here is 0.62, and he's 34 inches tall. Which of the following is closest to the mean of the height distribution? So we're looking for the mean, but unfortunately they did not give us the standard deviation or the mean. Now the mean for both of these are equal because it's from the same distribution, and the standard deviation is equal. Whenever I have one of these problems, I like to go ahead and write z equals x minus mu over sigma and figure out what I actually have. Well, in this case, I'm looking for mu. I don't know the standard deviation, but x is 32. And I also have this area, so I can calculate a z-score. So second vars, inverse norm, 0.32, mean is 0, standard deviation of 1, and I end up getting a negative 0.4677. I'm going to write that down. Negative 0.4677. And that's my z-score. If I do the same thing over here, I have 34 minus the mu over the standard deviation. And second vars, inverse norm, 0.67. And I look and I have 0.4399 for my z-score. And it makes sense that I'd have a positive z-score because I'm over halfway, where here I'm below halfway. So I have a negative z-score. Unfortunately, I'm missing the standard deviation and the mean, but I know that they're the same. And then I recognize something about algebra. And yes, I get to do a systems of equation because I have two equations here and I have two unknowns. So I'm going to rearrange this. I'm going to have negative 0.4677 sigma, just multiply both sides by sigma, equals 32 minus mu. Doing the same thing over here, I have 0.4399 sigma equals 34 minus mean. Now I'm going to go ahead and combine these equations. So I have negative 0.4677 sigma equals 32 minus the mu. And when I combine them, I'm just going to swap the signs of the lower. So this becomes a positive, this becomes a negative, and this becomes a positive. Well, now my means drop off, and 34 minus 2 is 2. And if I add plus the original one, excuse me, clear that real quickly. So 0.4399, 0.4399 plus 0.4677 equals 0.9076 sigma equals 2. And then I'm going to divide both sides by 0.9076. And so 2 divided by 0.9076 equals the standard deviation, and I think I've made an error, so I'm going to pause for just a moment to undo this for just a second. All right, I did make an error. I put in 0.67 and I should have been using 0.62. So I need to change this to 0.62. It still makes sense as it's positive, but I had the wrong value. This should have been 0.3055. So this is also 0.3055 plus 0.4677. So I end up getting 0.7731, and so I end up with 0.7731 sigma equals 2. I'm going to divide both sides by 0.7731. Excuse me, 2 divided by 0.7731 equals, the standard deviation equals 2.5867. So I get a standard deviation of 2.5867, but that's not what I'm looking for. But that will help me get the answer that I need. What I need is the actual mean. So I can plug into either one of these. So I'm going to go back to this 0.3055. So we have 0.3055 equals 34 minus the mean over 2.5867. Because all I did was plug in what I know. So times 0.3055, subtract 34, and I get negative 33.21 equals negative m. Make both sides positive, and I end up getting 33.21 equals m. So 33.21 equals m, and my best answer is D. Once again, since I messed it up earlier, I'm going to redo this part real quickly. Second vars, inverse norm, 0.32 gives me negative 0.4677 as a z-score. Second vars, inverse norm, 0.62 gives me the 0.3055. Okay, and then you solve it using a system of equations, and if you don't make a mistake like I did, you're going to get a standard deviation of about 2.58, 2.59, and then I can plug back into either this equation or this equation, it doesn't matter which one, and I will get about 33.21, or D is my answer. All right, moving on to number 32. A company ships gift baskets that contain apples and pears. The distributions of weight for apples, the pears, and the baskets are approximately normal. The mean and standard deviation for each is shown in the table. The weights are assumed to be independent. That is critical because they're going to ask us to combine standard deviations, and we cannot combine standard deviations or variances if they're not independent. They told us they were, so we're good to go. Let the random variable W represent the total weight of 4 apples, 6 pears, and 1 basket. Which of the following is closest to the standard deviation of W? Well, to do this, I need to add up all my apples. So I have apple 1 plus apple 2 plus apple 3 plus apple 4. Now, obviously, I can add up means directly, but with standard deviations, I have to square them. And by the time I get this far, it's like, you know what? I don't need to write this 4 times. I can just go 4 times 0.2 squared. And with the pairs, I actually have to do this technically 6 times. So that's going to be 0.18 squared plus 0.18 squared. And pretty soon I get smart and go, how about you just do plus 6 times 0.18 squared? Unfortunately, we only have the 1 basket. So plus 1.88 squared. Please remember, To combine standard deviations, you must convert them to a variance and then add them. And once you've done that, then you can take the square root. So 4 times 0.2 squared plus 6 times 0.18 squared plus 1.88 squared. All right, now I'm going to take the square root of that, caret 0.5, and I get 1.97. So my standard deviation for the basket with everything in it is 1.97 ounces. Okay. All right. So once again, 0.2 squared plus 0.2 squared plus 0.2 squared dot, dot, dot. 0.18 plus 0.18 plus dot, dot, dot 6 times. So this is my 4 times the 0.2 squared. This is my 6 times my 0.18 squared. This is my basket. Apples, pears, basket. Okay. All right, next question, number 33. Researchers will conduct a study of television viewing habits of children. They will select a simple random sample of children and record the number of hours of television the children watch per week. The researchers will report the sample mean as a point estimate for the population mean. Which of the following statements is the correct for the sample mean as a point estimator? First off, the sample mean X bar is unbiased from you. X bar is unbiased from you. All right. Alternatively, P hat is unbiased for P. So a sample of size 25 will produce more variability than for the estimator than a sample of size 50. And that is true. We have more confidence when we have a larger sample. This has more variability. So this is a true statement. This is probably our answer. We're gonna keep going on. Sample size 25 will produce less variability. That's false. A sample of size 25 will produce a biased estimator. No, it won't. The mean X bar is an unbiased estimator. A sample of 25 will produce a more biased. No, it won't. X bar is an unbiased estimator. A sample of 25 will produce a less biased, not a factor because X bar is unbiased. So our best answer is A. All right. 34. 34 is an easy question, but people miss it because they didn't bother to memorize their formula. This is an easy one. A research study indicated a negative linear relationship between two variables, the number of hours per week spent exercising and the number of seconds it takes to run one lap around a track. Computer output from the study is shown below. Assuming all conditions for inference are met, which of the following is an appropriate test statistic for testing the null hypothesis that the slope of the population regression line equals 0? All right, so they're telling HO, the null, beta equals 0. HA, beta does not equal 0, where beta is the slope of the regression line. All right, well, for this problem, T equals our sample slope divided by the standard error. That's simple. Well, what's our sample slope? Exercise time, so equals negative 2.20 over, what was our standard error? And I'm not seeing it. There it is, 0.07. Because it's straight across this line. All right. So with that being the case, the answer to 34 is D. All right. The answer to 34 is D. Once again, I just looked at the slope and it's like, all right, this is my slope line. And I know that because constant is my y-intercept. This will always be my y-intercept. So this is my slope. That's my numerator. This is my denominator. And you're like, what about the sample size and square root of 11? Because they said size. They've already taken account that when they did this, created the standard error. So you're good to go. You just need B over the standard error. Number 35. The table below shows historical data for the distribution of the number of customers in half-hour time periods who visit the electronics department of the retail store. For example, 25% of the time periods for which data were collected, no customers were observed in the department store. To investigate if the distribution has changed. As soon as I see this, that is key phrase. They want to know if the new distribution, how it compares to the old distribution. If I'm comparing distributions, this is going to be a chi-squared and probably going to be a goodness of fit. All right. So we have an old distribution and we have this new distribution. This is what we observed. All right. So this was historical. This is what was observed. So a chi-square goodness of fit test was conducted to determine whether the data value provided convincing evidence that the distribution has changed. The test statistic was 10.13 with the p-value of 0.0175. Which of the following statements is true? Okay, that's a pretty small p-value, all right? So at the significance level of 0.05, by the way, I should say this, the chi-square goodness of fit, HO, the null, the distribution matches the historical, HA, the distribution does not, the distribution changed. But the distribution is the same as the historical, the distribution has changed. So we have a small p-value, which means I'm going to reject the null and say the distribution has changed. At the significance level of 0.05, the data provide convincing evidence that the current distribution is different from the historical. I like that. That's probably my best answer. Let's continue. At the significance level of 0.10, the data do not provide. No, they're definitely small. 0.01 is definitely smaller than 0.1. So there's definitely convincing evidence. The mean number of customers in a randomly selected time period is 12.5. I'm not even sure why they asked that. All right. I'm not sure where that came up, where they came up with that. No valid conclusion because the observed frequency for one cell is less than 5. This is a critical thing. Observations can be less than 5. Expected values cannot be less than 5. So if my expected value is less than 5, I have a problem, but I can have observed values that are less than 5, no problem with that. The chi-squared has 50 minus 1 or 49 degrees of freedom. No, chi-squared goodness of fit, or the Goff degrees of freedom is categories minus 1. So cat minus 1. And we have 1, 2, 3, 4. 4 minus 1, in this case, 3 degrees of freedom. All right. So the only possible answer is A. Number 35. The answer is A. All right. Number 36. This is a challenging problem. Made me think earlier this evening. Suppose that 25% of women and 22% of men would answer yes to a particular question. All right. In a simulation, a random sample of 100 women and 100 men were selected, and the difference in sample proportions of those answering women minus men was calculated. So basically, we're expecting 0.25 minus 0.22, which gives us a difference of 0.03. The process was repeated 1,000 times. Which of the following is most likely to be representative of the simulated sampling distribution of the difference between the two sample proportions? All right, so what we know is the expected difference is 0.03. So this is what we should be centered on. We should be centered on 0.03. And that's kind of great because I look at this, that's not centered on 0.03. That gets rid of E. I look at C, that's not centered on 0.03. So that gets rid of that. I look at D, That's also not centered on 0.03. When I get to A and B, A is clearly centered on 0.03, and D might be, because that's like 0.05. So this could be centered on 0.03 as well. So I can't just say it's A, I can't say it's B, I'm gonna have to do some more work. Well, to do that, I'm going to actually have to calculate my standard deviation for the difference of mean. Now, I'm going to need to go x1 plus x2 over n1 plus n2. Well, x1, we're expecting 25 women plus 22 men, 100 plus 100 equals 47 out of 100. Excuse me, 47 out of 200. I forgot, can't do real fractions here. 47 divided by 200. And I get 0.2354. So my p hat combined equals 0.235. So now I need to go and do my standard error. My standard error formula is p hat combined, q hat combined over n1 plus p hat combined, q hat combined over n2. Essentially, that's 0.235 times 0.1 minus that. I'm not feeling very smart right now. Set 0.765 plus 0.235 times 0.765 all over 100. Okay, so 0.235 times 0.765 times 2, because I got to do it again, or plus itself, it doesn't matter. And then I'm going to divide by 100. Then I got to take the square root of that. So I'm just going to raise it to the half power. And I end up getting about 0.06. I recognize it says it's 0.0599, but I'm going to say that's about 6%. Okay, so we're dealing with a normal curve. So if we're starting off as a center, we know our center is going to be 0.03. We know we have a center at 0.03. We're going to have 1, 2, 3 standard deviations this way, 1, 2, 3 standard deviations this way. 0.03 plus this is 0.09. That's adding to 0.06 because we said our standard deviation is about 0.06. Then I do this again at 0.15. Then I get 0.21. Well, this looks better than A. B looks better than A because look, I have a bar at 0.1, we have 0.9. I have one at 0.15, we have 0.21. Going down, I have negative 0.03, negative 0.09, negative 0.15. This one has the negative side. This one doesn't even have a negative side. A is not correct. B is my best answer, and that is a challenging problem. But basically, we calculated the mean, and we calculated the mean by going 0.25 minus 0.22 equals 0.03. That gave us the center right here at 0.03. Then we used our formulas, and basically we had to go, all right, our formulas, what were they? P hat combined equals x1 plus x2 over n1 plus n2. And then we had to use the standard error formula, P hat combined, Q hat combined over N1 plus P hat combined, Q hat combined over N2. And that gave us our standard error. That ended up being the 0.06, which helped us find our answer. All right, challenging problem. Problem number 37. Making sure I didn't skip one, just a second. Did not. So problem number 37. According to the government data, 22% of children in the United States under the age of 6 years live in households that are classified at a particular income. So here's the claim, P equals 0.22. A simple random sample of 300 children in the United States under the age of 6 was selected. So now we have a sample of 300 was selected for a study of learning in early childhood. If the government data is correct, so if this is correct, which of the following best describes the probability that at least 27% of the children in the sample live in households that are classified at the particular income level? All right. So we want to know what's the probability that we get a p hat of greater than 0.27. All right, greater than or equal to 0.27. Well, z equals p hat minus p naught over p naught q naught n. Please pay careful attention to the formula. So p naught is, or p hat is 0.27. That's from the sample. The claim is 0.22, so minus 0.22 over 0.22. 1 minus 0.22 is 0.78 over 300. Now, the reason I knew to use 22 here as opposed to 27 is the formula said to. It said use the population value. Use the population value. Do not use the sample. The sample value goes here, but it does not go in the denominator. All right. So that's why I knew that this is 0.22. Consequently, my answer to number 37 is, excuse me, I swapped the order. This is correct. My answer to 37 is B, which is what I actually wrote, but not what I was circling. So 0.27 minus 0.22 over the square root of P naught, Q naught, and N. All right, moving on to number 38. The machine is designed to dispense at least 12 ounces of beverage into a bottle. To test whether the machine is working properly, a random sample of 50 bottles was selected and the mean number of bottles was computed. So basically, now that we have a sample size 50, we know that we're normal by central limit theorem. The hypothesis is mu equals 12. The alternative is mu is less than 12, where mu represents the population mean number of ounces of the beverage dispensed. The p-value for the test was 0.08. Which of the following is the most appropriate conclusion to draw at the significance level of alpha equal 0.05? So we have a p-value and an alpha. Well, we do have a reasonably small p-value, but it happens to be greater than alpha. So we're going to fail to reject. We have insufficient evidence to reject. Because the p-value is greater than the significance level, there is convincing. No, there is not convincing. That is wrong. Because the p-value is greater than a significance level, there is convincing evidence. No. Because the p-value is greater than the significance level, there is not convincing evidence that the population mean number of ounces dispensed into the bottle is less than 12 ounces. Winner, winner, chicken dinner, number 38, C. All right. Number 39. In a certain school, students can choose whether to eat in the school's cafeteria. A reporter working for the school's newspaper polled students on their reactions to changes in the menu at the cafeteria. For each student leaving the cafeteria in one 30-minute time period, the reporter used a coin to determine whether to stop the student and ask how he or she felt about the menu. In the reporter's article, it was stated that a random sample of the students showed that 89% of the school student population was happy with the new menu. Now let's talk about this real quickly. Did he do a random sample? Yes, he did. Did he do a random sample of the entire school? No. He actually did a random sample of those in the cafeteria. All right. So that might play a impact on this. Because each student leaving the cafeteria was randomly selected and could choose to answer or not, this is a random sample. If they're allowed to choose or not, that's bad. All right. So this is not good. You're not allowed to choose to answer not. If you do that, you're going to have non-response bias. Because students self-selected whether to eat in the cafeteria, the sampling method might be biased and the sample might not be representative of all students in the school. That's a serious issue there. That could be the case. All right. Because he only surveyed those in the cafeteria, they were already destined to eat there. So those who didn't eat there obviously didn't want to eat there in the cafeteria. All right, number 40. Ms. Tucker travels through 2 intersections with traffic lights. Oh, we got 2. Anytime we have 2, we're looking at some sort of table or sample space. The traffic lights operate independently. That's usually important. The probability that both lights will be red when she reaches them is 0.22. The probability that the first light will be red and the second will not be is 0.33. What's the probability that the second light will be red when she reaches it? Well, let's talk about this. We have the first light. First light. Red, not red. We have a second light. And it's either going to be red or not red. All right. And it says the probability that both lights will be red when they reach them is 0.22. So both red is 0.22. And that wasn't conditioned to anything. It just said they're both going to be red. The next thing, the probability that the first light will be red and the second light will not be red is 0.33. First light is red and second light is not red is 0.33. Once again, they didn't say given that or if that, it was just, this is a fact. So this is a joint probability. And I can add these 2 up together and get a marginal. So I get a marginal of 0.55. What is the probability that the second light will be red when she reaches it? Well, that's this, and I don't know that value. And normally I'd be stuck, but they told me something. They said that they were independent. And if they're independent, I can say, hey, the probability of A times the probability of B equals the probability of A and B if they're independent. That's only true if they're independent. So I can go 0.55, that's this value, times my X has to equal my intersection. And I know that's my intersection because that's where it crossed. Doing some fancy algebra, I'm going to divide both sides by 0.55. And I get X equals 0.4. And so my answer to number 40 is A. All right. Once again, this times this will equal this if they are independent, but only if they're independent. So that's what I use. This times this equaled the intersection. And I knew that because they told me up in the scenario that they were in fact independent. Thank you.